I know it's the fourth day, and it's going to be a longer day than yesterday, but we'll have a nice dinner as a treat in the end. So you have to stay till the end. But let's get started with first invited talk by Markus Lohrey. Markus did. I have to continue this theme. He did the tour of Germany in a way. He studied in Nuremberg and then did his PhD in Stuttgart.
Erlangen, actually.
Really?
No, I studied in Erlangen.
Oh, okay. Very
close. Very close.
Yeah. More hops on the tour. And he was in Leipzig as a professor, and then Siegen now. And he's working on various topics that are closer to this community than I think many people realize. I've been beating the drum for applying AofA techniques more on the space usage of things than on time, not in a replacement for the former, but I think it's much easier to make the case that we want the precise results that we can get if it's about space than about time, because for various reasons, people care more, and it's easier to pin down what model makes sense. Counting bits is pretty universal. So in that theme, I think the talk will ring a few bells and others. It's not about compression only, it's also working on the things when they're compressed. Over to you, Markus.
Yeah, thank you very much, Sebastian, for the nice introduction. It's great to be here. It's my first AofA, and yeah, I'm learning a lot. So yeah, it's about grammar-based tree compression. But before I start with trees, let me first talk about grammar-based string compression. And yeah, what is grammar-based compression? Well, grammar-based, I will explain it, as I said, with strings, with the example of strings. And the idea is basically to compress a string by a grammar. In this case, for string, it's a context-free grammar. Oops. Yeah, so it's a context-free grammar that produces exactly one string. Yeah, usually a context-free grammar produces a set of strings, but here we consider context-free grammars that produce only one string. So if you are not familiar with context-free grammars, don't worry. On the next slide, you will see an example, and I think then it will become clear. So this idea goes back to some of the pointer. Yeah. Goes back to Storer and Szymanski from '82, from a paper. And here's the formal definition. So a so-called, yeah, we call these context-free grammars. They are usually called straight-line programs, and I always use the abbreviation SLP. So this is a context-free grammar G in so-called Chomsky normal form that derives a unique word, and this unique word is denoted as the value of G. And so what does this mean? This means in a context-free grammar, if you're familiar with, you have so-called non-terminals or variables and terminal symbols. And for the variables, for every variable A in the grammar, there's a unique production where A is on the left. So A derives BC, where BC are two other non-terminals or variables. And then there are also these productions here where a non-terminal A derives to the terminal symbol little a. And then there are no cycles in the derivation. That means from a non-terminal A, you cannot apply rules for a certain time and arrive at a word which again contains the same non-terminal A. So there are no cycles in the derivation. Okay, so this, as I said, don't worry if you're not absolutely sure about what this means. I will show you an example on the next slide. The size of such a straight line program G is simply, well, the number of variables or the number of productions. I mean, that's a sensible size measure. All right, good. So this was the formal definition. So let's look at an example. So I just listed here the productions of the grammar. So here, the red one is the start non-terminal. You have to specify where you start with. So I start with A, and then A is replaced by BC, and then you continue with B. B is derived to CD, and C is derived to DE, and so on. And at a certain point, well, then you derive the terminal symbol. So E, the variable E derives to little b, the variable F derives to little a. And you see there's no cycle. Yeah, if I start, let's say, with A, you cannot go back to A. It's acyclic. And let's see what the word derived by this straight line program is. So we start with A, then, as I said, the rule for A is BC. So we replace A by BC. So what I'm showing here is the so-called syntax tree, right, of the grammar. And so B is replaced by CD, and C is replaced by DE, and so on. And at a certain point, you have replaced all variables by these terminal symbols, yeah? And the word, the value of this straight line program is simply the word B, A, B, B, A, B, A, B, right? So that's the value. So if this is, let me call this straight line program here G. Usually I use the letter G for grammar, right? It's a grammar. So it's this word, yeah, so this one. And the size of the straight line program is 6 because I have 1, 2, 3, 4, 5, 6 rules. Rules, productions, that's the same, right? I use both terms usually. Okay, good. It's clear? Yeah, good. And a good point of view is to look to view such a straight line program by a DAG. Namely, the DAG is here shown on the right. There I mean, this is the syntax tree, right? And the syntax tree is huge. Yeah, it can be very big because you can double in each step, you see. But this DAG contains for every variable, so A, B, C, D, E, F, a unique node, yeah? And for the two terminal symbols, little b and little a also. And then I have left edges so the variables are the inner nodes. And every variable here has a left outgoing edge and a right outgoing edge. And it's obvious, it flows from A, the left edge goes to B, this one, and the right edge from A goes to C. So this is this edge here, right? And I mean, of course, this syntax tree is just what is called the unfolding, yeah? If you fold it, well, unfold it, it's a reverse, yeah? So you unfold it to this syntax tree here, right? That's a good viewpoint. Yeah, it's a DAG, directed acyclic graph. Yeah, where every inner node has one left edge and one outgoing right edge. Okay, good. Yes? Yeah, you can do this, and sometimes it's defined. So here, this is what is called Chomsky normal form, right? And some people don't require this. It's convenient, and of course, you can easily assume it. I mean, if you have a long left-hand side, you can break it up. And yeah, the point is, if you would allow general production, then you should define the size of the grammar in a different way by summing up. You would then take the sum of the lengths of all right-hand side. This would be the reasonable size definition then, yeah? Yeah, let's assume this, yeah. I'm generating one string, yes. Yeah, one string, yeah. Fun?
That grammar will have some number of productions that is, given this instruction form, will have some number of productions relative to the length of the string.
Yes.
Whatever.
Yeah, of course. I mean, it's obvious if you have a word of length n, yeah, you can to n minus 1, yeah, probably, right? Would be that's trivial to achieve, right? With basically, then you have no compression. I mean, the point here is compression, and that's the next point. So I'm claiming that a straight line program G can indeed be seen as a compressed representation of value G. Remember, value G is the string derived from G, and I will give good reasons for that in a moment. A grammar-based compressor is then an algorithm that computes from a given word W, a hopefully small straight line program G that produces W. So that's grammar-based compression. And this is not pure theory. I mean, this is actually done. So there are examples of grammar-based compressors that are really used. The most famous one is probably AofA24, which is really used. I forgot where, I think GZIP, or I'm not sure. But there are some compressors based on AofA24. Well, originally, AofA24 is not formulated as a grammar-based compressor, but if you look at it, what you actually do is you produce a grammar for the input string. Then there are others like dissection, repair is also quite famous. Sequitur. So there are many grammar-based compressors, and so this is somehow really used. But now let's make this point that you can compress with these straight line programs. Let's make it a bit more precise. So for that, let me fix a word W of length n, and with little sigma. So it's a word over the alphabet, capital sigma, and little sigma is the size of this alphabet. The number of symbols, that's also important sometimes. Okay, good. So these are the two parameters, n, the length, and the number of symbols, sigma. And with optimum or opt W, I denote the size of a smaller straight line program for W. That's a fixed number, yeah? It's not unique, probably, the smaller straight line program, but it exists. And well, first of all, we already said there's a trivial upper bound, which is linear in n, right? 2n something or 2n minus 1 probably. Depends on how you define exactly the size of the grammar, but here it's the number of productions or rules. A trivial lower bound is the logarithm of n. Yeah, you cannot be better, right? This is also somewhat obvious, because the syntax tree is a binary tree with n leaves. So the height must be log n, and you need at least that many variables. So this is also not really surprising, this lower bound. Now, what about non-trivial upper bound? And there's a first result going back to Berstel and Brillig from 1987. So what did they show? They showed this optimal size is some constant, and multiplied with n divided by the logarithm of n, but the logarithm to the base sigma, the size of the alphabet. Of course, I'm assuming here that the alphabet has size at least 2. Yeah, okay. Right, so this is a non-trivial upper bound. Yeah, and we will come back to this result when we talk later about trees. There are several proofs actually. Actually, this upper bound can be also obtained using AofA24 actually, yeah. And for instance, you can find a different proof. For instance, there's this book on information theory, Gover Thomas, I think. There you can find a proof of this upper bound based on AofA24 compression. So good. All right, so this is an upper bound. So in some sense, you can always compress with straight line program. Of course, you can assume, but wait, this is not possible. You cannot compress every string, because if you could, then you could compress the compressed representation again and again and again. Of course, this result here is only true because I defined the size of the straight line program as the number of productions. But if you want to produce a binary encoding of the compression, then you get again back this logarithmic factor, right? So therefore, this is not a contradiction to a simple counting argument that you cannot compress everything. Good. All right. So another important thing is the smallest grammar problem in this context. So this is now an algorithmic problem. So I give you a word W, and the goal is to produce a smallest straight line program. Remember, opt W is the size of a smallest straight line program for W. That would be good if you have an efficient algorithm for that. Yeah, that's actually, I mean, that's what we would like to do. But there is also classical result by Charika and a long list of co-authors from 2002. Namely, this problem cannot be solved in polynomial time unless p equals np. So there is little hope of coming up with a polynomial time algorithm for the smallest grammar problem. And it's even worse, unless p equals np, there is no polynomial time algorithm that produces for a given word w a smaller straight line program, which is by a admittedly quite small factor, only larger than the optimum. So what do we have here? 8,569 divided by 8,568. This is greater than 1, right? So therefore, it's an improvement over the first. It's a stronger result than the first statement. Where does this strange number comes from? So they use an approximation lower bound for vertex cover, I think. Yeah, I think it's vertex cover. And then, of course, there's a reduction. For vertex cover, there's also similar approximation lower bound, but there the number is larger, not so strange. But then of course, Charika, they make a reduction, and that blows up this approximation factor. So that's the reason for that. Okay. So what is the best positive result in this setting? This is also goes back to Charika. There are alternative proofs by Wojciech Ritter and Arthur Jesch. Namely, they showed there's a linear time algorithm that produces from a given word w of length n a straight line program of that size, so up to constant factor. Again, here you have the optimal size, and then it's bigger by a logarithmic factor. So you can approximate smaller straight line programs up to a logarithmic factor, logarithmic in the length of the input word. Yeah, that's the best we know, and it's in this set context, in this area, it's a major open problem, of course. Yeah, either to improve this result, this logarithmic factor, or well, yeah, also to improve the lower bound. This is open.
Well, what's your guess? Where does the
Ooh, I have actually no guess here. I mean, one might expect that this is not the real truth, right? But I don't know, actually. I have no intuition here. What's the truth? Yeah. Difficult. Yeah. Okay, good. Right. So what else? Yeah, this is also a result. I will come back to it in the second part, but I first would like to mention the string result. So balancing. What it means balancing. So from a given straight line program G, again, now we have to be, okay, now little n is the size of the straight line program, right? And W is the string derived, or the word derived from G, and it has length capital N. So capital N usually is much larger than little n, yeah? And from the straight line program, we only have the straight line program G. We do not have W, right? And we cannot produce it in polynomial time because it can be huge, W. So we can produce in time linear in the size of the straight line program, a new straight line program H, such that the following is true. So first of all, H and G produce the same string. All right. H is only by a constant factor larger than G. Little n is the size of G. We have a constant blow up. I think it's 12. Well, in our proof. So, and now the important thing is the depth of H. So what is the depth of H? So as I said, remember, a straight line program is basically a DAG, and it's the height of the DAG or the height of the syntax tree. Yeah. And the point is that this depth is logarithmic in the size of the string derived from G or H. It's the same, right? Yeah. This is, of course, the best you can achieve, logarithmic height. Yeah. because the syntax tree, I mean, it's a tree with capital N many leaves, the syntax tree, so the height must be logarithmic. And this is a very useful result. And because in many algorithms, basically what you do is you run down in the syntax tree. Here's a simple example, random access on compressed words. So what we can do with this result is we can, from a straight line program G, we can build in linear time a data structure, which is basically H, the balanced straight line program. And and this data structure allows to solve the following problem. So W here is again the string derived from G. So I give you a position in the word, and you want to simply output the ith symbol, yeah, right? The ith symbol. And this can be solved in time logarithmic in the length of W. Yeah, remember again, W is too big. I mean, you cannot produce an array containing W. Not feasible, yeah? Okay, and there was this result was known before we proved this result, this balancing result, but I would say the proof is much more complicated. It uses several ancestor data structures, and they are, it's a stack of data structures. It's really a quite long and difficult proof, the original proof by Bille, and I would say this is simpler here. All right. I mean, this is a simple corollary, right? I mean, basically you produce the balanced straight line program H, and then you have to compute for every variable, for every non-terminal of H, you have to compute the length of the string derived from that non-terminal. And using these lengths, if you want to compute the ith symbol here, it's clear you walk down in the DAG. Yeah, that's what you do. It's a very straightforward algorithm then. Okay, good. So I think that was all I wanted to talk about strings. And now we come to the actual talk, namely grammar-based tree compression. And this is divided into two parts. And in the first part, I will also briefly talk about DAGs. And DAGs, directed acyclic graphs, I mean, in the context of tree compressions, they already were shown here at this conference. Stefan gave a talk on the average size of the minimal DAG of a tree in the binary search tree model. And he mentioned also that DAGs are used for string compression, and I just want briefly talk about it. So first of all, let's fix the trees. I mean, there are many kinds of trees in the world. And what are the trees that I will consider here? I will consider rooted trees where nodes are labeled. And the labels, they come from a certain alphabet gamma symbols of labels. And every node has an arbitrary number of children, so not necessarily binary trees, any number of children. And they are ordered, so plain trees where the plain rooted trees where the symbols are labeled. These are the trees that we will consider here, right? And directed acyclic graphs, well, it's a standard way to compress such trees. What the idea is simply if a fringe subtree appears several times, has several copies within the big tree, then you represent it only once. And here is an example. So this is a tree, right? And you see, for instance, there are several, BA here has 3 occurrences. You represent it only once. And probably you can do some other compression. And this would be the DAG, a DAG. Yeah, if you unfold this DAG here, then you get again this tree. Yeah, so this here you fold it, and here you, in the other direction, you unfold it. Yeah, I hope this is clear, and I don't have to define this in a more formal way. So this is the DAG. And actually, well, this is what I would call the minimal DAG. Yeah, because there's no more folding that I can do. Yeah, it's the smallest DAG that represents this tree on the left. Okay, good. You might ask about what has it to do with grammar-based compression. Well, in some sense, this DAG is also it's a so-called regular tree grammar. This is not really important, but let me briefly explain what I mean by that. So the nodes of the DAG can be viewed as non-terminals of a grammar, and actually and the productions are of this form. A derives to, so a variable derives to a symbol from the labels. So this is a node label, A1 to AK. And what do I mean by that? This is the DAG from the previous slide. And let me name the nodes. So this is node A, this is node D, B, C, E. And then this is the corresponding grammar. Y, A, node A is labeled with D, and it has 3 children. The first children is node D. You have it here. The second children or child is node B. And the third child is C. Yeah, and similarly, so these are the rules. This is, of course, the same description as this DAG in principle, right? So in this sense, DAGs are a kind of grammar-based tree compression. Whether this is a good grammar-based tree compression, we will see, but it is. We don't need them, no. Yeah. No. I don't know. I actually later I will skip them. Yeah. Pardon? They must be ordered. Yes. If you draw this stack, it must be. This is the first edge. So you would give the numbers, right? You would label this one 1, this edge 2, and this edge 3, because the trees that I want to consider are ordered. Yeah, the order of the children matters. So the DAG must be also ordered then. Yeah. The letters could be anywhere. You mean here little a? You have to distinguish here. This is just a name for the node, and this is a label, right? And so the label, different nodes like A and B can be labeled with little d. Fun?
I'm talking about the labels.
Yeah.
You have a label A, a child label B, and then a child label A.
Oh yes, everything. Yes, they can all have the same label. Then it's in principle an unlabeled tree. I mean, yeah. Everything can be labeled the same. With this, these rules, you mean? Well, I don't know why. Yeah, of course, there should be no cycles here, right? Yeah. It must be again acyclic in a sense. Yes, it's an acyclic. It's not an arbitrary regular tree grammar. There's a formalism of regular tree grammars, and there you can have for one symbol here on the left-hand side, you can have several rules, and there can be cycles, and it produces a set of trees then, a set of trees. Yeah, of course, I need, again, this acyclicity condition and determinism that for every symbol here, there's exactly one rule, right? It's very similar to the straight line programs for strings in some sense, yeah? Very similar. Anyway, this is not really important. This viewpoint. I just wanted to mention it because it's called grammar-based tree compression. Good. Then, so clearly every tree has a unique, well, it's not, okay, I mean, in principle, you could ask for a proof, but it's, every tree has a unique minimal DAG, yeah? You simply merge nodes in which isomorphic subtrees are rooted as long as possible. It's uniquely defined. And let me mention this old result of Downey, Sethi, and Tarjan from 1980. You can compute this minimal DAG actually in linear time very efficiently. Yeah. This is of course good. And I also want to mention, because it's combinatorics, of course, is important here, and you should always mention something of which goes back to Flageolet. So this is the slide. Namely, you can be interested in the average size of the minimal DAG taken over all trees of size n under a certain distribution. And the first thing is, of course, take the uniform distribution. And Flageolet, Sipala, and Stewart, they did it for binary unlabeled trees. And well, here we consider node-labeled plain trees, where the number of children of a node is arbitrary. So you might ask, what is the average number of nodes of the minimal DAG for a uniformly chosen tree? I just say tree in the following. Always means plain, rooted, plain, labeled tree. So of size n with k many node labels. K many node labels, yeah? And it's, well, it has this characteristic n over square root log n behavior. And the constant depends on k. It's this one, square root of ln 4k over pi. I think for, this is twice, of course, okay, if you want to have unlabeled trees, simply set k to 1. And I think the constant is by a factor 2 larger than the constant for binary unlabeled trees. Yeah. Okay.
So in your case, when you have 1 on 10.
Yes, yes, of course. Then you see basically you get here, Then this ln and this cancels and you get something linear, right? Then of course the DAG is trivial. We cannot do anything. Yeah. Yeah. Okay, good. Yeah, similar results. I mean, Stefan talked about this, and he mentioned also Luisa Seebach-Benkner. He just did her PhD. You have seen her, the cake, exactly the cake, yes. And they proved similar results for classes of random tree models, yeah, so-called leaf-centric tree sources, more general results. Sometimes these general results do not yield the exact constant. So there is still some ongoing research here. Good. And now we come to the real part. The real grammar-based tree compression. So first of all, we have seen in the first part, we have seen straight line program for strings. We have seen some nice results. Remember, there was this result that you can always achieve, in some sense, some compression. The size of a smaller string straight line program is was this n divided by log n. And we had also these balancing results. And such results, they are not true for DAGs. You cannot balance a DAG in some sense. Yeah, this is not possible. Okay, you can ask, what does this mean? But this is, I just mentioned this because this is the motivation for looking at something, a kind of grammar-based tree compression where all the nice results for strings carry over to trees. And these are so-called forest straight line program. So first of all, somehow it's useful to consider forests instead of trees. This will be useful to take this more general point of view. So what is a forest? A forest is just an ordered sequence of trees. Yeah, it's ordered. Yeah, so if you have tree T, tree U, and you write here T, here U, it's not the same as when you exchange them. It's an ordered sequence of trees. So the order of the roots is important. And the point now is, again, for string straight line program, the main thing about these straight line programs for string is the concatenation operation. Yeah, you have rules. And what a rule is basically doing, it takes two strings that are already there and you concatenate them. Yeah, this is the basic thing, concatenation. Now for forests, there are two useful operations for building up larger forests from smaller ones. And we call these two operations horizontal and vertical concatenation. And I introduced them with small examples. So this operator here, it's called, this is just a symbol we use for the horizontal concatenation of two forests. And what is it doing? It simply takes the first forest, the second forest, and puts them next to each other. Yeah? You get a larger forest. So here's an example. So this is a forest consisting of two trees. This tree, an A labeled node with two children, B and C. And this is simply B. This is a node of size 1. Yeah. And here is another forest consisting of one tree, B with 3 children, C, C, B. And what do? You construct a new forest by, and this one. The first forest is A with B, C, then here the B, and here this tree is here. And important, again, the order here is important. It's important. Yeah. This is horizontal concatenation, and this is only possible because we consider forests. Otherwise, if you take two trees and you concatenate them, it's no longer a tree. It would be a forest. Yeah. Now, this operation alone would not be very useful for constructing big forests from smaller ones. We need also, of course, if there is a horizontal concatenation, there must be a vertical concatenation. And for vertical concatenation, we have to, that's a bit technical maybe, we have to consider so-called context. So this is a context. A context is a forest. Well, here the forest consists of only one tree, but there could be more trees. But the important thing is there is one specified leaf in the forest. One specified leaf, it's labeled with the star here. It's a kind of, you can view it as a forest with a hole. This is a hole. And in a hole, you can put something, another forest. And the other forest is the one on the right. So what is this kind of forest? Vertically, this is vertical composition, concatenated with this one. It's this forest. In this example, it's again a tree where I put this forest below this node here, below this node. You see, what I simply do is I take this one and replace it by the star here. So this forest here, the blue forest you have here. And of course, the two roots here become children of the parent node of the whole. Yeah. So therefore, these A and this A, these two nodes are children of this one. Yeah, that's what happens. This is vertical concatenation. Yes. No restriction. It can be everywhere, anywhere, but it's only one hole. Yeah. So we call this a so-called context or forest context. It's a forest where exactly one leaf is labeled with the special symbol star. Star is not in gamma. Gamma is the set of other labels. That's a forest context for us. It's a forest with a hole where a specified position where you can plug in another forest. Yeah. Okay, good. Right? So this is vertical concatenation. This is important, yeah, that you understand this operation. Exactly one. This is somehow, you could argue why there could be several stars, and then this would lead to some unpleasant effects. So therefore, we don't allow this. Okay, good. Now, a different point of view is, of course, forests and forest context can be also written as expressions with parentheses. So here, forest, this is a forest, and here I don't use commas. So here you see this is a forest consisting of 3 trees. This is the first one. This is the second one. Yeah, you have to match the brackets, and this is the last one, consists just of an A. Yeah, I just write the trees in the forest in left to right order, and this is a forest context where I have one specified position where the star sits. Yeah, and then these operations are very simple. I mean, horizontal concatenation is just textually you write the two forests next to each other. So you write F followed by G. It's like string concatenation. And vertical concatenation means you take the first forest, and there where the star is here, you just plug in G. You write at that position, you replace the star textually by G, simply. Good. Now, the next thing are forest algebra expressions. And what is a forest algebra expression? Basically it's an operation. It's an expression, like an algebraic expression, using these two operations. So, and we start. So a forest algebra expression is an expression that is built from these constants. So what do I use? What constants do I use? Alphabet symbols. So little a here is from gamma, right? And then I also need a with a hole, a star. Yeah, these are also constants that I have to use. Yeah. And I use the binary operations of horizontal and vertical concatenation. Yeah. So the constants are a, just a, and a with a hole below a. That's the two constants that I have to use. So basically, when you want to construct a tree with such a forest algebra expression, these are the leaves. These are used for leaves, and these constants are used for the internal nodes. We will see an example on the next slide. But you cannot write any forest algebra expression. You cannot write any expression using these operations. It must be well typed in the following sense. So let me write F for the type of forests and C for the type of forest context. So remember, C, these are the things with the star, with the hole. And these guys here, they do not have a hole. And these are the possible ways I can use these binary operations. I can concatenate horizontally two forests. I can horizontally concatenate a forest with a context, or the other way around, a context with a forest. But I'm not allowed to horizontally concatenate two contexts, because then I would have two stars, and I don't want to have it. Yeah. So C horizontally concatenated with C is not allowed. And how can I use this operation? Well, if I have a context, I can plug in a forest. That's what we do, right? We have a context, there's the star, and I plug in a forest. Or I can also take a context and plug in vertically another context. Then I have again a context, right? We have the context, there's the star. You replace the star by another context, then you have again a context. Okay, but you cannot, the left argument has to be a context. You cannot take a forest because then there's no specified position. There must be the star. Okay, if this is a bit unclear, let's look at an example. Okay, yeah. Now, what is a forest straight line program? Let me first say this. This is a forest algebra expression which is represented as a DAG. Yeah, that's the compression. Let's look at an example. Here I have a tree. Well, I call it a forest since I'm talking about forest straight line program, but for simplicity, I just have one tree here, right? There could be several trees, but I have only one. And now, this is a forest algebra expression. And if you evaluate this expression, you get the tree on the left. So you see what happens here, for instance. A star, remember, A star it's the same as A with a hole Or if you draw it as a tree, it would look like this. Yeah? So, and we have it here. Yeah? So, here's A star. And there we, for the star now, for this star, up here. For this star, we plug in the tree that you obtain by evaluating this expression. Yeah. So this expression here evaluates, no, sorry, it's a forest. Yeah, this is a forest. If you evaluate this expression here, then you obtain the forest consisting of this, the tree rooted here and the tree rooted here. Yeah. Okay. So for instance, this node here corresponds to this leaf if you really do the evaluation. This B evaluates to this node, right? They correspond to each other, right? Yeah, here I use vertical concatenation, so A star B. Basically, that gives you these two nodes here. So A star horizontally concatenated with B gives you these two nodes here, yeah? And there you plug in something below, namely this forest, and so on. Yeah, you can do this evaluation. Yeah, this is an expression. If you evaluate it, you get this tree. And now you see in this tree here, there are many repetitions. There are many subtrees which are the same. So basically, I mean, this tree has roughly the same size as this tree. It's even larger because you have all the internal binary nodes. So it's double. The number of nodes here is twice the number of nodes here. So therefore, we represent it by a DAG, and that's a forest straight line program. Yeah. Okay. That's it. Okay. Questions?
So why in the tree in the middle there is an A star? So I would assume in that algebra you don't have like endpoints with stars.
So you see that the A star, you're asking about the A stars. These are all the A's here, right? Yeah. There are 1, 2, 3, 4, 5 A's here, and you have A star here, 1, 2, 3, 4, 5. They correspond to each other. But these are A stars because you have to, yeah, because they are the internal nodes, right? I mean, if you evaluate this expression, then you have to plug in something into these A's from below. That's the point, yeah? Yeah?
Just another. So imagine the forest basis.
In the forest here, yeah? Yeah? Then there would be an A here also, yes. If this would be, for instance, if you replace this B by an A, then there would be an A here. Yes, yeah. Okay? No. Good. Right, so forest straight line programs. And as for strings with value G, I denote the forest produced by G. By this forest straight line program. This is just a forest produced. Good. And there are two related formalisms, so-called tree straight line programs we defined much earlier. They are basically used for binary trees. It's related, but I think this forest straight line formalism is a bit more general and maybe also more elegant, but it's a matter of taste. And there are so-called dot DAGs, which were introduced by Bille and some co-authors, and they are very similar to forest straight line program, actually. Let me just remark, a string straight line program is basically a forest straight line program that only uses the constants A, not these ones, and horizontal concatenation. It's basically a forest of one node trees. Good. So now some results. So the first one is there is an algorithm, a linear time algorithm that produces from a given tree or forest, if you want, of size n with k different node labels, a forest straight line program of size And by the way, the size is, what is the size? I haven't defined the size of a forest straight line program. Let me briefly go back. It's the number of, let's say it's the number of nodes in this stack here. Yeah, that's the reasonable size measure. Yeah, okay. So that's the size of a forest straight line program, the size of the compressed representation, and we can we can come up with a forest straight line program of size constant times n divided by log n, the logarithm to the base k. We have k different node labels in our forest. So this is, of course, completely analogous to the result for strings. And for DAGs, something like this is not true. Yeah, okay. Let me say a few words about the proof. So how does it work? So what we do is we partition the input forest F in a first step into clusters, the forest, the input forest, or tree. Usually we want to compress trees, but of course we are dealing with forests. So we partition the input forest of size little n into clusters. In the size, these clusters, they are sub-forests and sub-forest contexts. I will show you an example. Maybe that makes it a bit more clear what we mean by that. And the number of clusters is n over L for some carefully chosen L. And the size of the clusters is between L and 2L. So basically, whenever we can glue together two clusters of size at most L, we glue them together, because then we are still below 2L. And then, so we have to choose L carefully, namely as something linear. The constant here has to be chosen carefully. I think it's something around 1/2. We choose L as the logarithm of n to the base k. And then you can show, well, if you choose L carefully, then you can show that the total number of forests and contexts of size in this interval, there are not too many then. This is linear in n over log n k. And then simply we have two parts. The forest straight line program consists then of two parts, and both respect our size bound that we want to achieve. Namely, there's a forest algebra expression for the forest obtained by contracting all the clusters from step one. Yeah, you contract those clusters, you obtain a tree basically of that size, where L is log n to the base k, and this is a tree, and basically we just take any forest algebra expression for that tree, and then we take a DAG producing all the subforests and contexts for all the clusters, basically, yeah, for all the clusters. So let's look at an example. Here we have a tree, we want to compress it, and this might be the clusters from step one. So here this L could be 1, because all clusters have size at most 2L, you see. Yeah, I don't want to define it in a more precise way how to come up with these clusters, but then what we do is we contract all the clusters, and you see many clusters appear twice, like here, this cluster here appears twice. This is the B here. So B is basically an abbreviation for this cluster. A is this one, and so on. And all these clusters can be produced by forest algebra expressions. So for instance, this cluster is produced by this forest algebra expression. There's a mistake here. This must be C star. Must be C star, because I take C star and I plug in below A star. Then I get this cluster. Yeah. This one is A star horizontally concatenated with B. Yeah. And it appears several times. And then you see there's the same information. Yeah? You can recover the tree, the tree on the left from this description here. And then you simply produce any forest algebra expression for this tree. You can take this one. It looks complicated now, but this is just I don't do any compression here. Yeah, simply for each in some sense, sequentially, you produce this tree by some forest algebra expression. These would be the rules. So this is a very rough sketch, I admit, but that's it. And this is again the result. Speed up a little bit. And there is related work. So we can use this, or we use this for universal tree coding in a subsequent paper. And of course, you should also always mention one organizer. There's a very similar approach was used by those people, including Sebastian and Ian also. I mean, this two-step approach, this is not new, yeah? And this was used many times, including this paper. The difference is in your paper, the clusters are used, you use a Huffman encoding for these clusters, right? That's it. And this was also used for universal tree coding in combination with efficient querying. Okay, let me skip this because I just want to mention some, how much time do I have? We started a little bit later, maybe.
We leave some time for questions, maybe 5 minutes.
5 minutes is okay, fine. Let me just mention a few other results. So again, remember, there was this result that the smallest string grammar, or string straight line program can be approximated up in linear time, even up to a logarithmic factor. And again, the same result carries over to trees. So forests, there's a linear time algorithm that produces for a given forest of size n, a forest straight line program of this size. So this is the size of a smallest forest straight line program for f. And then you have the logarithmic factor. Another result is the balancing result that also goes through. Namely, given the forest straight line program G of size n, producing the forest f, the value of G. And this is much bigger, of course. Let's again say this has size capital N. Then you can compute in linear time, linear in the size of the compressed representation, the forest straight line program. You can compute a new forest straight line program H. They produce the same, they are equivalent. H is only by a constant, small constant factor larger than N at, well, 12, I think, something like in our proof. This can certainly be improved. But the important thing is that H is again a DAG. Yeah, a forest straight line program is a DAG representation of a forest algebra expression. And this DAG has again a height. And this is again logarithmic in the size of the forest. As you see, you can, with these forest straight line programs, you can get a balanced representation of forests. Yeah, which is nice. Again, this can be used for algorithms. Again, you can do some kind of random access. For instance, if you have a forest straight line program V that produces a forest F, and I give you a pre-order number of a node V in the forest, and you want to compute a label. This can be done again in time logarithmic in the size of the uncompressed forest. Yeah. Good. I think, forest straight line programs in database theory. This is a very recent work. Basically, 2 minutes. What we do is we specify queries. We have a forest and we have a query language. And a famous query language is MSO. And what such an MSO formula, what is it used for? Let me just briefly go over it. We have a forest F and we have such a formula monadic second order formula phi with a free set variable x. Yeah, it's a free set variable x. So x, for this x here, you can plug in a set of nodes in F, and then you can define the query result. It's the set of all node sets A in the forest where the formula is true. This is a typical database theory problem. And in database theory, you want to enumerate all these sets. You want to efficiently enumerate them. Now there are many of these sets. There are many. And the question is then, what does it mean to enumerate all these sets? Well, what we can do is the following. The forest F now is specified by a straight line by a forest straight line program, compressed. So F is given in compressed form. And starting with the compressed representation of F, we can compute a data structure in linear time. And with this data structure, we can enumerate all these sets A, where the query is true, in so-called output linear delay. That means for the computation of one of those query results, A, where phi is true, the time we spend for it is linear in the size of A. Yeah? That's the best you can basically achieve. So this is called output linear enumeration. And a special case is, for instance, if these sets all have constant size, then you have so-called output constant constant delay enumeration. And that's something which is quite often wanted in database theory, but I have to go over that. Sorry for that. Spend too much time with the strings, probably. Here, I want to end with this slide. This is actually a slide for string compression. And here you see many areas that I haven't mentioned here in the talk, but you see straight line programs have many connections. For instance, in algebraic complexity theory, they appear in verification. There are some recent applications. I mentioned information theory, string data structures is quite obvious, but also in group theory, yeah. We are working on that. You have many nice applications of straight line programs for in group theory, efficient algorithms. So that's it. Thank you.
Oh, any questions on that?
Okay, I'll start here.
Hi. Nice talk, Markus. You can expect this question. What if you have some model to probabilistically generate the strings, and then you compute things like what's the expected size of your FSLP, things like that? Are there results in this line? I guess not many, because that's quite recent, right? So
let me maybe let's maybe go back to strings. It's a bit easier, but anyway, you see everything that holds for strings here also holds for forest. So for strings, I mean, I guess what you mean is, or what you're asking about, I defined for strings. I defined this the size of a smallest straight line program for W. And you're asking about the average size of W of this value. If W is, let's consider all binary strings of length n, and then you are interested in the average size of W, right? Am I right, roughly? Or some others, yeah. Yeah, the point is you have this upper bound here, right? On the this is a worst case. This is always true, right? That means when you encode the straight line program by a binary string, then this factor basically cancels out, and you get something linear in the size of n. And you know, almost all strings in information theory, we know from information theory, almost all strings of length n are incompressible. So you cannot expect much. So if you would, the simplest setting, choose W uniformly. Let's fix the alphabet, binary alphabet, to make it easier, and choose W uniformly among all strings of length n, then the average will be the same. Yeah. So.
But still, we don't know the constant.
Yeah, the constant could be, yes, yeah, maybe the constant could be. I even don't know what the constant here really is, but you have to look up in the proofs. Yeah, the constant could change. Yes.
About this bound and the bound in your main result, are these bound sharps? And if so, what strings or what forests in your main result do attain this bound?
So you mean whether this bound is sharp?
Sharp, yeah.
So certainly not for all strings.
No. But is what do the strings or the trees or forests in your main result look like that have exactly this bound?
Yeah. For instance, there's a nice example where this bound is sharp. So De Bruijn sequences. You take a De Bruijn sequence of length n, where all you take all subwords of length log n, and they all appear, right, or something like that. So a De Bruijn sequence, they basically
Similar construction for trees, I guess.
Yes, you can do a similar construction for trees. I mean, another answer, but a stupid answer would be take a Gorov random string. That's also then, but De Bruijn sequences give you a more explicit example. Yeah.
Okay, so we had a last person in the queue that was over here, and I forgot who was asking. And if not, maybe in the interest of time.
Thanks, Mark. Thanks, Mark, for the talk. I have a question. If I understood correctly, the results for woods and forests are quite similar.
Very similar, yes.
How the proof works? Do you have some correspondences between your coded forests as words or vice versa? There is some bijections, I don't know, some transformation.
So yes, I mean, of course, not surprisingly, the proofs for trees and forests, they are also similar. It gets normally a bit more technical for forests, but I'm not aware of a formal correspondence really. Well, for this balancing, I mentioned this balancing result. And there actually we have a more general framework. You can do this balancing in principle for general algebraic structures. You have operations and you can build up algebraic circuits and you can try to balance these circuits. And indeed, there we have some general conditions that allow to balance circuits in the way we did, so that the height of the circuit gets logarithmic. And strings and forests are two examples. So indeed, there is something more formal, but this is only true for this balancing result. Yeah.
Okay, well, thank you very much, Markus.